Section 1. At 5 times the speed of sound, the V-2 rocket was invisible until the moment of impact, when the first operational missile struck Chiswick, London, in September 1944. It heralded the dawn of the space age, with a terrifying thunderclap. But if we look away from the crater and trace the trajectory backward past the launch pad, into the factories, and through the supply ledgers, we find a radically different story. We find a program that cost approximately 2 billion Reichsmarks, a massive capital investment rivaling the Allied expenditure on the atomic bomb. Yet, unlike the Manhattan Project, this investment did not end the war. Instead, it arguably accelerated the collapse of the investor. Now, let's open the operational records and analyze the systems that defined this campaign. The V-2 program serves as the ultimate historical warning on the perils of distorted resource allocation. In the final years of World War II, the German industrial machine was not defeated solely by Allied strategic bombing or battlefield losses, but by an internal cannibalization of its own assets. When we analyze the production charts from 1943 to 1945, we witness a decision-making process that completely divorced technological ambition from logistical reality. The leadership sought a wonder weapon to bypass the strategic deadlock, but in doing so, they initiated a supply chain crisis that would starve their defensive capabilities. The core logistical challenge here was a classic zero-sum game played within a closed economic loop. Germany was operating under a strict, shrinking resource ceiling, a finite amount of high-grade steel, rare earth metals, chemical propellants, and skilled labor. Every resource allocated to the V-2 program was a resource explicitly denied to the conventional Wehrmacht. This was not a situation where the state could borrow against future surplus. Every ton of steel used for a rocket combustion chamber was a ton of steel subtracted from tank production or submarine hulls. To the engineers at Peenemünde, the V-2, technically the Aggregat 4, was a triumph of aerodynamics and propulsion. But to a systems analyst, the rocket was a logistical parasite. It required delicate gyroscopes, vast quantities of liquid oxygen, and an ocean of ethanol. We are looking at a logistical footprint that was disproportionately heavy compared to its tactical yield. While the propaganda machine promised a miracle weapon that would turn the tide, the supply chain managers were staring at a mathematical impossibility. They were attempting to sustain a futuristic aerospace program while their conventional forces were literally reverting to horse-drawn transport due to fuel shortages. The V-2 program forces us to confront a critical inefficiency: the pursuit of a breakthrough capability that compromises the fundamental stability of the entire organization. This is not just a story of a rocket. It is an autopsy of an industrial suicide. Section 2. The strategic logic behind the V-2 was born of desperation and defined by asymmetry. By 1943, the Allied bomber offensive was systematically dismantling the German surface industry, and the Luftwaffe had effectively lost air superiority over Europe. The German High Command faced a bleak equation. They could no longer match the Allies plane for plane or tank for tank. They needed a bypass mechanism, a weapon that operated outside the conventional theater of engagement. The V-2 was not merely a weapon. It was envisioned as a psychological breaker, a technological sledgehammer designed to pummel London into submission without risking a single German pilot. The operational plan, championed by Armaments Minister Albert Speer and the rocket engineers, hinged on a premise of overwhelming volume. The goal was not a handful of prototypes, but a ceaseless rain of ballistic missiles. The production targets were staggering. The initial plan called for the manufacture of nearly 12,000 rockets per year, eventually ramping up to a target of 900 to 1,000 units per month. To achieve this under the constant threat of Allied bombing, the entire industrial apparatus was forced underground. The production lines were moved to the Middlework facility, a vast, subterranean factory carved into the Kohnstein Hill in the Harz Mountains. When we analyze the blueprints of this operation, we see a fatal collision between the complexity of the design and the brutality of the manufacturing environment. The V-2 was an incredibly sophisticated machine, consisting of over 30,000 individual parts. It required precision welding, delicate gyroscopic guidance systems, and turbopumps capable of pushing fuel at immense pressures. Yet, the plan attempted to treat this aerospace marvel like a mass-produced artillery shell. The leadership assumed that if they simply allocated enough raw space and labor, the output would follow. However, operational records reveal a chaotic industrial reality. The move to underground facilities protected the assembly lines from bombs, but it created a logistical nightmare for the flow of materials. We see a supply chain that was fragmented and brittle. Subcomponents had to be transported from across the shrinking Reich to this central node, creating a bottleneck where any delay in a single electrical relay or valve halted the entire line. The manufacturing process was plagued by a lack of standardization and skilled labor shortages, leading to a high rate of technical failure before the rockets even reached the launch pads. Furthermore, the decision to prioritize the V-2 created a bureaucratic war for resources within the German military-industrial complex. The plan did not exist in a vacuum. It had to fight for the same electrical components used in radar systems, and the same aluminum used in the Messerschmitt fighters. We find in the archives that the V-2 program was granted S priority, the highest tier of procurement importance, effectively allowing it to commandeer resources from other vital sectors. This was the core strategic delusion, the belief that a singular, high-tech priority could override the fundamental laws of industrial capacity. The leadership believed they could simply order innovation into existence at scale, but by demanding mass production of a prototype technology in the middle of a collapsing infrastructure, they were not building a reliable weapon system. They were constructing a logistical sinkhole that would swallow the very materials needed to defend the factory gates. Section 3. To truly understand the scale of this logistical disaster, we must strip away the aerodynamic cowling of the V-2 and examine the machine not as a weapon, but as a consumer of high-value assets. When we isolate the V-2 as a logistical unit, we are confronted with a machine that was arguably the most expensive single-use item in human history up to that point. This was not a reusable asset like a tank or a fighter jet, which could perform hundreds of sorties. This was a complex, 12-ton assemblage of precision engineering designed to destroy itself in a fraction of a second upon arrival. The primary enabler of the V-2 was its propulsion system, a marvel of rocketry that demanded an exorbitant chemical tithe. The engine consumed a fuel mixture of liquid oxygen, A-stoff, and ethanol, B-stoff. When we analyze the supply chain required to feed this engine, the data becomes startling. The ethanol required was not a byproduct of the petrochemical industry. It was distilled from agricultural produce, specifically potatoes. Operational records indicate that a single V-2 launch required approximately 4 tons of ethyl alcohol. To produce this quantity, the German agricultural sector had to process roughly 30 tons of potatoes. In a vacuum, this is a fascinating conversion of biomass to thrust. But in the context of 1944 Germany, a nation facing severe food shortages and rationing, it was a caloric catastrophe. We see a direct, horrifying conversion rate. The fuel for a single rocket launch consumed the caloric equivalent of daily rations for thousands of civilians. By scaling this to the thousands of rockets launched, we realize the program was effectively distilling the nation's food supply into a propellant that would simply burn up in the stratosphere. However, the alcohol was the manageable part of the equation. The true logistical nightmare was the oxidizer. liquid oxygen, or LOX. Handling LOX on an industrial scale in the 1,940 seconds required a level of infrastructure that Germany could barely support. Liquid oxygen boils at -183 degrees Celsius. It cannot be stored for long periods. It is constantly evaporating, a phenomenon known as boil-off. When we map the logistics of the LOX supply chain, we see a system fighting a losing battle against physics. The production required massive amounts of electricity to run the cryogenic plant's electricity that was desperately needed for the aluminum smelters and synthetic oil refineries. Once produced, the LOX had to be transported in specialized, insulated rail cars to the launch sites. Throughout this journey, the inventory was shrinking by the minute due to evaporation. Our analysis suggests that for every ton of LOX injected into a V-2 combustion chamber, nearly 2 tons had to be produced at the source. This is a logistical efficiency rating of nearly 50% loss before the weapon is even fired. The enabler here was a leaking bucket, draining the national power grid to produce a resource that vanished into thin air if not used immediately. Beyond the fuel, we must look at the structural costs. The V-2 required high-grade aluminum and magnesium alloys for its airframe to withstand the aerodynamic stresses of supersonic flight. It utilized specialized graphite vanes for thrust vectoring within the exhaust plume components that required rare materials and precision machining. But the most critical component was the guidance system. Each rocket contained a complex set of gyroscopes and accelerometers. These were not mass-produced stamped metal parts. They were delicate instruments, requiring the finest craftsmanship and high-purity metals. If we compare this to the alternative enabler of the time, the V-1 buzz bomb, the disparity in resource allocation is staggering. The V-1 was a crude cruise missile made of cheap sheet metal, powered by a simple pulse jet engine that ran on low-grade fuel. It cost approximately 3,500 Reichsmarks. The V-2, by contrast, cost roughly 38,000 Reichsmarks, more than 10 times the price, yet delivered the exact same 1-ton warhead. From a systems analysis perspective, the V-2 was a negative-sum enabler. It required the highest tier of metallurgical inputs: aluminum, high-grade steel, the most energy-intensive chemical inputs, LOX, ethanol, and the most skilled labor inputs, gyroscope assembly. In exchange, it delivered a payload capacity that was negligible compared to the resource investment. Every time a V-2 lifted off from a mobile launcher in The Hague or the Eifel Mountains, it was carrying a 1-ton warhead. But to deliver that 1 ton, the German war economy had expended the resources equivalent to several fighter aircraft. The system was designed to deliver high-tech explosives, but in practice, it was a mechanism for destroying Germany's own high-value inventory. The V-2 was not just a weapon. It was a furnace that burned the very materials the Wehrmacht needed to survive the ground war. Section 4. When we perform a systems autopsy on the German war economy of 1944, we are not looking at a system with slack capacity. We are looking at a system operating at its absolute elastic limit. To understand the true cost of the V-2, we must move beyond the financial cost and analyze the displacement effect. In a command economy under siege, money is irrelevant. Materials and man-hours are the only currency that matters. When we overlay the production data of the V-2 program against the struggling output of defensive armaments, we see a clear, inverse relationship. The V-2 was not an addition to the Wehrmacht's arsenal. It was a subtraction from the Luftwaffe's survival. The first incision in our autopsy reveals the critical hemorrhage in the electronics sector. By late 1943, the Allied bomber offensive had shifted to night raids and bad weather bombing, relying on radar to find targets. Germany's only hope of defense lay in its night fighter force, equipping planes like the Ju-88 with sophisticated Liechtenstein airborne radar sets. These radar sets required high-fidelity vacuum tubes, complex wiring harnesses, and precision potentiometers. When we map the supply chain, we find that the V-2's guidance system was a voracious competitor for these exact same components. The analog computer inside the rocket, the Mishkaret, and its associated gyroscopic stabilizers absorbed a massive percentage of the electrical engineering industry's capacity. Historical analysis suggests that for every V-2 guidance unit assembled, the electrical components for a potential night fighter radar set were effectively consumed. The system prioritized a blind weapon that hit random London suburbs over the precision sensors needed to blind the Allied bomber streams, destroying German industry. We see a direct displacement. The capacity to shoot down bombers was traded for the capacity to dig craters in residential neighborhoods. Deeper into the autopsy, we find the opportunity cost of the propulsion research. The German aerospace industry was simultaneously developing the Messerschmitt Me 262, the world's first operational jet fighter. This aircraft was a true game-changer. It was 100 miles per hour faster than any Allied piston-engine fighter. However, the Me 262 was plagued by delays, particularly in the reliability of its Junkers Jumo 004 jet engines. These engines required high-temperature alloys, specifically nickel and chromium, for their turbine blades. While the V-2 primarily used steel, its program held the S priority rating, allowing it to monopolize the best metallurgical engineers and testing facilities. More critically, the Wasserfall, project a surface-to-air missile, derived from V-2 technology, was delayed and eventually abandoned in favor of the ballistic missile. Systems analysts argue that the Wasserfall, which was smaller, radio-guided, and designed to detonate amidst bomber formations, was the defensive weapon Germany actually needed. It would have utilized the same rocketry principles but with a tactical purpose, protecting the oil refineries and factories. Instead, the V-2 program displaced this defensive capability, redirecting the rocketry talent toward a strategic weapon that had no impact on the enemy's ability to wage war. We must also analyze the warhead dilemma. The V-2 delivered a 1,000-kilogram warhead. In the final year of the war, the German chemical industry was suffering from a catastrophic shortage of fixed nitrogen and explosives. The demand for artillery shells on the Eastern Front was insatiable. Yet, the V-2 program demanded a specialized casting of high-grade explosives, often triolin, a mixture of TNT, hexogen, and aluminum powder, to ensure maximum blast effect. When we calculate the logistical return on investment, LROI, for these explosives, the numbers are damning. A 1,000 kg warhead on a V-2, landing randomly in London, might kill 2 or 3 civilians and destroy a row of houses. That same ton of high-grade explosives, if loaded into anti-aircraft shells or anti-tank mines, could have destroyed multiple Allied tanks or bombers, directly degrading the enemy's combat power. The system was taking its scarcest resource, high-yield explosives, and firing it into a strategic void. Furthermore, let us revisit the liquid oxygen infrastructure with a wider lens. We previously established the electricity cost of producing LOX, but we must contextualize it within the energy ledger. The electricity used to run the cryogenic compressors for the V-2 program was electricity not powering the synthetic oil plants. By 1944, the German army was largely immobilized by a lack of fuel. Tanks were abandoned on the roadside. Pilots were grounded. The V-2 program's electricity consumption was a parasitic load on the energy grid, indirectly throttling the production of synthetic gasoline. The system was burning electricity to make rocket fuel, while the tanks protecting the borders ran dry. Finally, we trace the human element. The V-2 program absorbed the intellectual capital of the Third Reich. Thousands of the brightest physicists, mathematicians, and engineers were sequestered at Peenemünde and later in the Mittelwerk complex. This was a brain drain of epic proportions. These mines were not working on proximity fuses for anti-aircraft guns, better radar countermeasures, or acoustic torpedoes for U-boats. They were solving the problems of supersonic flight, a scientific achievement, certainly, but a military irrelevance in 1944. The system's autopsy concludes that the V-2 was not merely a waste of resources. It was a blockade runner against its own supply lines. It cannibalized the electronics of the night fighters, the metallurgical potential of the jet fighters, the explosive capacity of the artillery, and the energy reserves of the synthetic fuel industry. The German war machine did not just stumble. It tripped over its own wonder weapon. Section 5. When we tally the final ledger of the V-2 program, the numbers present a devastating indictment of strategic mismanagement. Approximately 3,000 volts, 2 rockets were launched against Allied targets. While they caused terror and tragedy, killing an estimated 9,000 civilians and military personnel, their impact on the outcome of the war was statistically negligible. In military logistics, we look for a force multiplier, an asset that creates an advantage far greater than its cost. The V-2 was the exact opposite, a force divider. It took a massive slice of the German war economy and converted it into a weapon that could not hold ground, destroy supply lines, or stop a single enemy tank. The verdict of history is clear. The V-2 was a technical triumph that masked a catastrophic failure of resource allocation. The German leadership fell victim to the sunk cost fallacy. On a national scale, having invested heavily in the research during the early years of the war, they felt compelled to push the weapon into mass production, even when the strategic context had shifted entirely to defense. They prioritized the potential of a future technology over the reality of the present crisis. This case study stands as a stark warning about the dangers of dysfunctional innovation. In any complex system, whether it is a military campaign or a modern manufacturing firm, innovation must be integrated with the core operational capacity. The German High Command allowed their R&D division to cannibalize their operations division. They chased a silver bullet solution, believing that a single technological leap could bypass the hard math of logistics. But logistics is unforgiving. By starving the conventional army of steel, fuel, and electronics to feed the rocket program, they accelerated the collapse of the very front lines that were protecting the rocket factories. For the modern supply chain manager or executive, the V-2 offers a timeless lesson in opportunity cost. It demonstrates that high-tech investment is not inherently valuable. Its value is determined by its alignment with immediate strategic goals and logistical constraints. If an organization invests in a revolutionary new system but depletes the resources needed to maintain its core deliverables, it is not innovating. It is liquidating. The V-2 proved that you cannot bomb your way out of a supply chain deficit. And you certainly cannot win a war or a market by bankrupting your own infrastructure to build a product that arrives too late to matter. The ruins of the V-2 factories leave us with a profound truth that resonates far beyond the battlefield. They remind us that the most seductive trap in strategy is the promise of a miracle cure. True resilience isn't found in the breakthrough weapon that drains the system, but in the disciplined management of the resources we already have. When we chase the perfect solution at the expense of the essential foundation, we don't build the future, we dismantle the present.